что у вас Черман? Да ладно, я могу так начать просто, без Чермана. Я могу без всякого Чермана начать, да. All right, I think
Good morning.
Yeah, let's start it. So we keep talking about K-theory of projective space. So maybe I'll write specifically. So P n. This is what? This is the quotient. So that has homogeneous coordinates. Maybe x0, x1. So for xn, the homogeneous coordinates. So up to scaling. And then we have an action of this, of maybe let's consider diagonal matrices with eigenvalues a0, a1, so for an. So this is my torus A. And we have decided that the equivariant K theory of this projective space, these are polynomials in this ai plus minus 1 at one more variable, I think we denoted t plus minus 1, and mod out by the relation that the product of 1 minus ai inverse t inverse, that product equals to 0. Okay? So for instance, what is n equals 1? So n equals 1, that's a Riemann sphere. We usually use coordinate maybe x1 over x0. And so we'll have one point where x1 is 0. So usual coordinate maybe x1 over x0. And then infinity is where x0 is 0. And so in the relation will be two terms here, and their product is 0. But this is the class of this point. We talked about push forward. In particular point by push forward defines a class. We'll just take the Kazul resolution of that. So the class of this point, you think about what the Kazul resolution says. That is actually 1 minus, so this is where the second equation vanishes. So A1 inverse T inverse. And this point gives the class of this point is A0 inverse T inverse. And the fact that the product is 0 is just the fact that the 2 points don't intersect. Right? Make sense? So this is, each point defines a class, their product is 0, and that's the meaning of this relation. It's another meaning of this relation. And so if we do the same on n equals 2, so there'll be kind of coordinate lines. Maybe this is where, if this is x1 coordinate line, so means this is the coordinate where x2 is equal to 0. If this is x2 coordinate line, means x1 equals to 0. Maybe I should write it. Slightly smaller. X. So this is the line where x2 is equal to 0. This is the line where x1 is equal to 0. And we should add, in projective space, we should add the line at infinity, where x0 is equal to 0. And so, similarly, the classes of this, the classes of this each one of them, so this is something four-dimensional. Each one of this line is a copy of this projective line. Each one of them is a divisor in projective plane. The class of this is, well, the class of that is 1 minus A1 inverse T inverse, similarly so on and so forth. And so the equation that the product from I equals from 0 to 2 of AI inverse T inverse, that product equals 0, reflects the geometric fact that if I take the intersection of these three lines, that is empty. Clear? We also, by the same token, we can compute not just the classes of lines, but also the classes of points. What's the class of that point? This class of the point, well, the intersection of these two lines. So the class of this point is 1 minus A1T inverse times 1 minus A2 inverse T inverse, which is correct if you write the Kazul complex, which is resolution of the structure shape of that point, that would be the character of that complex. Because this is resolved. So we did Kazul complex, right? Well, how are we supposed to resolve the equation when x1 is equal to 0, x2 equal to 0? Well, we have two equations. We have two generators in the ideal, and there'll be one relation. The correct thing, right? Is that everybody with me? So now let's do one more step. And since we decided that if we want to do a covariant elliptic cohomology, then we don't talk about covariant elliptic cohomology. We don't have some ring. We have some geometric object. So if we want to think about this object geometrically, what we should think about is we should think about the what's the variety defined by these equations. And I will try to draw this variety as if I'm not in the multiplicative group instead in the additive group. So instead of trying to draw something which looks like a multiplicative group, I'll draw something like an additive group. So first of all, this everything lives over the base where I have two coordinates. So now I'm drawing spec. So this was the picture of P1 itself. And I am doing this spec. So that is to say variety defined by this equation. Spec of Ka P1. So what's it going to be? I have two coordinates. First of all, everything, it lives over, I don't know if it's such a good idea. Well, I'll try. So it will have two coordinates in the base called maybe A0 and A1. Right? And then one more coordinate, which is T. And this equation says that either T is equal to A1, A0 inverse, or T is equal to A1 inverse, right? So if I draw multiplicative group linearly, this would be the union of graph of what? So if I T equals A0, that's a function that goes something like that. So this is T. This would be a plane that goes. I'm trying to draw maybe. Yeah, well, that's what I'm trying to say. It's easier to work with additive. It's easier to draw additive group than multiplicative group. So this would be anyhow. This would be two planes. I won't be two. And they intersect. These two planes will intersect along the line that lives over where A0 is equal to A1. And so there will be another plane which is okay. We'll do a better picture in a second. So maybe better thing is to imagine, since this A's, A's overall the constant matrix is like trivially. So it's better to imagine that in fact we kind of mod out A's by the scaling. So there is a point where A0 equals A1, and over that, so up to if we project in the 1, 1, 1 direction, there will be a point where, so over the locus where A0 is equal to 1, these two things coincide. So you have T equals A0 inverse and T equals A1 inverse. And away from that, there's this term. Let's say there are two copies of the multiplicative group glued over the point where the two things coincide. And this is what the projection. So this is spec of Ka of P1. This is how it projects the spec of Ka of point. Okay. That clear? So now if I do the same picture I try to do the same picture. So this, I will need 3 planes, and I took some time to draw them ahead of time. This would look like this. So these are 3 planes that map. So if I think of this mapping to the A plane, there will be loci. There will be a locus where this A's, 2 of these A's coincide, and there's a locus where all of them coincide, and correspondingly, either 2 or all 3 planes here are glued. So if this is, for instance, if this is this point, the T restricted to this point, at this point, T is, remind you, that T corresponds to O of 1. Right? So this to say functions on the tautological line. Right? So at this point, this tautological line is the line of the form 0, 0. So the first 2 coordinates 0 and then something. Right? And so my torus on this line acts by multiplication by a. Oh, sorry. So this is, and then 0, 0. Okay, so x1 equals 0, x2 equals 0, and then x0 is anything. And so on this line, my torus acts with weight A0. Right? So on the dual space, therefore, it acts with the weight A0 inverse. So this point is the point where T equals to A0 inverse. So maybe I'll draw one of them and highlight one of them. Doesn't matter which one. Let's say this one. This is where T equals A0 inverse. And if I go to a different point, maybe I go to this point. This is here the line, here the tautological line is where this is x1 is 0 and x2 is 0. So this is the line. So x2 is 0 and x0 is 0. So it's this line. And so on this, so therefore here, the weight of my T is A1 inverse. So if I have another one, let's say this one. If this is the plane where T equals A1 inverse, then they intersect along so then the intersection between them, which maybe I'll draw corresponding indicate. So this is the line where they intersect. So this is the locus I do red and blue. So this is the locus where A1 is equal to A0. Right? And similarly. So is that clear? You can also, if you know toric geometry, you can also match this picture. So this is what's written here is the toric polytope. And if we look at the pieces in that picture and pieces in the toric polytope, then it's kind of reverses. The points corresponds to planes and somehow reverses the dimension. But if you, instead of a polytope, you think about the fan, then that's kind of dimension preserved. So. Now, if you look at this, you can say, well, I can certainly imagine what would be the elliptic analog of that? It's just right. So I already did, Andrei already pointed out, I already did a little bit of cheating by drawing multiplicative group additive. But I can write the exact same equation in elliptic for elliptic things, for product of elliptic curves. You take the exact same equation, look the exact same way. Okay? So the equation is, what does this equation mean? This equation means that t is equal to one of these guys. And that's the equation that makes sense. You can take a bunch of elliptic curves and glue them exact same way. That will be the spectrum for your elliptic cohomology. And if you did the toric geometry exercise, you can draw the spectrum of elliptic cohomology for any toric variety. That makes sense? Okay, so lessons from this. It has several important lessons. First lesson is that if I have some point here, some point in the base. So this is a point in the base. Here, in case of K theory, the base is actually the torus. The spec. So this is in K theory. That's actually the torus itself. And so I can take a point here and ask, what's its preimage? The preimage of this point can be what? Can be either 3 points, or a double point and a point, or a triple point, right? Because if I look at this point, what does it mean? If all a's are equal, if a0 equals a1 equals a2, well, equals whatever, constant. And what I'm looking at the equation 1 minus this constant inverse t inverse cubed, right? So this defines me a triple point. Right? So some equation to the third power equals 0. So I can, yes, please.
This map from the I overlap from the A point is a push forward?
No. That's the, so this is the, so the, there's a pullback on K theories, canonical, and so on spectra there's a map the other way. This is a canonical map. So this is, approximate, this is true in this example, but I write approximately, that the fiber over a point A is what? Is ordinary K theory of the set of points fixed by that element. So if depending where in this diagram is my point, so what does it mean? What does it mean 2 eigenvalues coincide? When 2 eigenvalues coincide, then the fixed locus of this thing jumps. Right? So if I have three different eigenvalues, that this will have, the corresponding element will have three fixed points. When is the line fixed? Additionally, is when 2 eigenvalues coincide. When is everything fixed? Is when the and to make this true statement, so it's a point in the torus. Oh, X is any space. So now I'm looking spec. Well, in this case, X is, in this example, X is P2, but in general, I can look at spec Ka of some space X. Here. And the general principle is that this is it. But I mean, to be exactly right, there's some kind of derived thing that needs to be done. And if you want to do an example, study the example. Very good example to study. Study the S1 equivariant K theory of S1 itself. So then if I forget, so inside of S1 there's and think about the point. So this is A. Think about the point equals density. But it's not for today. That's kind of important. That says that if I look at the current K-theory, that packages, in some sense, the K-theory of all fixed loci. In general, any kind of equivalent geometry should remember the ordinary geometry of fixed loci of all subgroups. Okay. That makes sense? Second important lesson is that this picture, this is the three planes glued together. Okay? They glued together over some subvariety in here. So it says away from some subvariety of the form, kind of AI equals AJ, or more generally, if I want to say, maybe more generally, I say, what's AI equal to J? I can rewrite it as AI minus AJ equals 1, and I can generalize it to be some kind of character of the torus, some kind of character b equal 1. Away from some such subvarieties. This is just the union of planes. So this is away from some such variety, the covariant K-theory of space X is in fact the same, just really the same, as the covariant K-theory of the fixed locus. This kind of follows from the first principle, right? Because if I look at the generic element, the generic element, the torus, will have some fixed locus, and that will be my generic fiber. Yeah, clear? So if I have some torus, the generic element there, all generic elements will have the same fixed locus because it's somehow by having some point fixed is an algebraic equation. So there'll be only finitely many types of any kind of fixed loci. So this will be generic one will have the fixed locus of the whole torus. And so therefore the generic fiber is just the K-theory of the fixed locus.
So K-theory of projective space equals to K-theory of a couple of points?
Away from this locus, it's equal, yeah. So a more mathematical way to say it, that we have two natural maps. So we have the inclusion of the fixed locus. So we have grand K-theory of X, grand K-theory of X. Then so there is a functorial. So there's an inclusion. There's a functorial map this way, which is the pullback. This is pullback functorial. And we've constructed the map the other way, the push forward. What is it? What does this map concretely? This map concretely here. So in this example of projective space, what does this map concretely have? If I have some polynomial, some kind of polynomial of t with coefficients in A, then in this pullback map, so what I do is I substitute. It's just a substitution of t. So you just compute. You take a tuple, you take f of A0 inverse and A, f of this A1 inverse and A, so forth. So I have a polynomial in one more variable. I have to introduce you here. So that's. And what's the push forward? Well, we also know what it is. If I take 1, so to speak, 0, that's the first marked point. Where is it going to go? Well, we computed that. So this would go to. This would go to. Well, we computed it over there. So that's a product from I, in this case, bigger than 0, 1 minus t inverse A I inverse. Right? This is to say this is a function. This is like the smallest possible function. So if I'm looking for a function that vanishes everywhere except at one plane here, that's the smallest one you can write because it has to vanish. It has to vanish at all other points. So that's where it goes. That's the push forward, right? Right? And then if we can compute the composition of pullback and push forward, so if we push forward and then pull back, what's it going to be? It's going to be a multiplication of when I stick this t back to A0, and this would be what? This would be this is the Thom class of the normal bundle. So normal bundle to the fixed locus. So this is to say, if I push it forward, pull it back, I'm going to get a product here. Concretely in this example, I'm going to get a product of 1 minus. Now C I inverse becomes A0. You divide by AI inverse. Product for I bigger than 1. These are the weights in the tangent space to this point. And this is the Kazul resolution at that point, because this is how torus weighs. This is how torus acts on the tangent. These are weights. Normal bundle, sorry, yeah, that's right. To the fixed locus in the. So this is weights of the action here. And so what does localization theorem says? That this map away from some subvariety, that's most map is isomorphism. More algebraic way to say it is that the kernel and co-kernel of both maps are torsion. That is to say, they're killed by some non-trivial polynomial in A. So this map is away. Both maps are isomorphism away from some sublocus. Means if I multiply any element in the kernel or co-kernel of this map is killed in this case. Well, in this case, it will be killed by the product of I less than j, because the equation of this locus is that. So this maps are on polynomials. They're not isomorphisms, but isomorphisms up to anything in the kernel or co-kernel of that is killed by some power of this thing. That's the localization theorem. And what's the proof of localization theorem? It's very simple. So it's not the mysterious result. So how do we define push forward? Push forward is defined by I take K theory of equivalent K theory of X by exact sequence that goes where are we going to go. So we have to look at the inclusion of the fixed locus. So this will take K theory. How does push forward work? We take a look at K theory of the Thom space for the inclusion of X, the fixed locus, into the whole thing. Right? And what's the complement of this? This is the set of non-fixed points. And this is the complement, so this goes to the K-theory of x minus the fixed points. Okay. Yep. Now, this map is always injective. So this is the push forward map. Why is it injective? Because this is injective. Because I ought to pull back, I ought to push forward, that's the multiplication by the theta of the normal bundle. But the theta of the normal bundle, by definition, has some torus weights in it. So this some expression has some non-trivial polynomial. That is not a zero. So this, what it does not divide zero. Okay. So if I have a map, multiplication by some element that doesn't divide zero, that has to be injective. This map has to be injective. If it's injective, means all the connecting maps are just zero. There's no connecting maps. All these maps are zero. And so then we have to look here. What's here? This is built. This has no fixed point. So this is built from, has no fixed point. So it means whatever torus orbits we have, they built by orbits A prime where A prime is not the identity group. Right? It has no trivial orbits. But equivalent K theory of, sorry, where A is not the whole group. Sorry, A prime is not the whole group. So it has no trivial orbit, not the whole group. But the K theory of this equivalent theory of A mod A prime, well, that's equivalent A prime theory of the point. So this is just functions on this A prime. What? No, just in general, if I have a K theory of a homogeneous point space, that's just that. And we never, this is just functions on this A prime. This never has the full support. This thing is always torsion. Means it's just killed by equations of defined A. So A is, any subgroup in the building group is defined by some character equal to 1. So this whole thing is killed by this then. So that's the end. End of the proof. And so now, when people learn this, they think it's the best thing since sliced bread, but it really is really powerful, because what does it say? It says that if I can, like for instance, let's just do it one more time. So just write the same thing one more time. Is that let's look at the, suppose we have A equivalent K theory of X, and suppose in here we have some element, some vector bundle, or whatever. Let's say vector bundle. It's a vector bundle on X. So, and if you suppose we want to compute, we have a map to the point, we can compute, we want to compute push forward to the point, which is this map. Where this goes to the Euler characteristic of this bundle. This is in topology, this is defined the way I explained yesterday, but in algebraic geometry, it's the ordinary Euler characteristic. In algebraic geometry, it's the ordinary Euler characteristic. So maybe some people were slightly worried about how this is going to work. But what's the Euler characteristic? Euler characteristic, if I have complex manifold, you can write this as an Euler characteristic of the Dalbo complex. You can, if you're on a complex manifold, you can say, well, I'm going to write my algebraic Euler characteristic using the Dalbo complex. Well, double complex is some complex of pseudo-differential operators, sorry, even differential operators, which I can, in the world of pseudo-differential operators, I can deform ad infinitum, as long as I've had some kind of deformation, what it means, to have a d-bar operator, you need some kind of notion of what it means to multiply by I. And so there's a purely topological definition, which is what we discussed yesterday. Right? So this is an element here. And we want to know what it is. Right? How we can approach this? Well, we know we have this guy here. Here, the push for it. So if we can write D as an image of something coming from here, then of course the map to the point, I might as well map to the point here. How am I supposed to write? How am I supposed to write V as an image? Well, I just use that equation. I have my equation, that tells me what it is. So it says, here, I pull back to the point, so I restrict my bundle to the point, but I have to divide by the theta of the normal bundle. And I can push forward that. So that is to say, I take the Euler characteristic of this on the fixed locus.
How do you know it is divisible?
No, it's not divisible. This is an equation. So since this is a non-zero divisor, we can divide by if we go to the open set, right? So this is some polynomial or some regular function. It's enough to know what it is on the open set. On the open set, this is divisible by that, so I can compute it. And so this is equality. It's especially powerful in the situation when this fixed locus is isolated, like in Nikita's lecture yesterday, you had this, somewhat complicated expressions in various things. But what the geometric meaning of them was there was some moduli space with a torus action. Its fixed points were isolated, were given by a bunch of partitions. And the computation on the whole space, you can do the computation on the fixed locus. So maybe I'll say it one more time. Many people, when they see this, they think, well, that's the end of geometry. You don't need to do geometry ever. You just write those expressions. But the point about geometry is that if you write those expressions at random, there'll be many, many poles to deal with. And so geometrically, you know that if you geometrically, you know that some meromorphic expression is in fact a regular function. And this kind of argument is extremely, even if you're just interested in applications to like integrable system, if you don't care about geometry, this kind of implication is extremely powerful. That you have some complicated expression. If you know that it expresses some notion which is geometrically defined, that will satisfy very nice properties. Like for instance, instead of being a meromorphic function, it's in fact a regular function. Yeah, Gus.
So in algebraic, well, that also involves familiar, you need some kind of properties or something about
Oh yeah, the push forward. That's right. We do compact manifolds now. Yeah. Yeah. Or compact topological spaces rather. Yeah.
In what sense would a characteristic lives in K theory of the point in the A equivalent?
Because if you think about, well, let's just do in algebraic geometry. So if I in algebraic geometry have some bundle on which the group acts, then the bundle will act on all cohomologies of that bundle. So the group acts, if a group acts on the bundle in over a compact space, then, right, sorry. While I remember, let me backtrack for a second, okay? So, yeah, one more point. This is what you should have stopped me at the moment when I used this normal bundle. Because this normal bundle here, this guy here, this is if it actually exists. Right? So in general, if X is some topological space, right? Then this Thom space, if I look at the inclusion of topological space in something ambient and contract the neighborhood, this will not be a Thom space of any bundle. Right? It'll be something which you can deal with that thing, but it's not going to be described by Thom isomorphism. If I include something singular into singular and I contract the complement, then who knows what's it going to be. Right? So it's important that this thing has a normal bundle. If it does have a normal bundle, we're good. If it doesn't, then separate study is required. Recommended. And strongly recommended, yes. Okay, so now back to the question. What was the question? Oh, the group acting. So if I have like suppose I have an algebraic variety. I have a group acting on some vector bundle on that algebraic variety. It will act on sections, it will act on cohomology, it will act on second cohomology, and so forth. So every cohomology will be a representation of this group. And if I take Euler characteristic, it's the alternating sum of cohomology, so it's a virtual representation of a group, so it's an element in K-theory of current K-theory of a point for that group. More questions? Oh. What you're saying is truth. Maybe it's not the complete truth. It's extremely important, right? So this is it's like Vanya correctly points out. You can solve kind of rather delicate number theoretic problems by knowing that some poles, by knowing that some integral, some kind of meromorphic expression comes from geometric considerations.
But what about the second part? That this is normal bundle. Is it double topologically it's clear, right? But we need to switch to algebraically.
Algebraic, it's the same. Algebraically, it's Thom space. You can define algebraically. It's some kind of it's whatever. It has some kind of. If you want, there'll be some kind of DG scheme, whatever. You need to know something about. You can. This thing also makes sense topology. So the general theorem of Thomason, extremely general theorem of Thomason, is that the co-kernel of this inclusion map, kernel co-kernel of this inclusion map, is torsion for extremely general schemes, and this applies to higher K theory and so forth. Okay. So now what we're supposed to do? We're supposed to study in these lectures. We're supposed to study Krichever genus. And so now maybe it's time I define it. So if I have what do I? Maybe I'll erase this symbol. Say what's again?
Euler characteristic is some kind of integral over X.
Yeah, there's something like an equivalent Riemann-Roch type thing. I don't really recommend doing it because in a current situation it will be a very complicated expression. You have to look at all kind of stabilizers and stuff. But in principle, there's some kind of you have to look at. It'll be some kind of integral over all fixed loci of all subgroups. It's kind of. I think it's. Some people like it. I've never used it in my life. So this is Riemann-Roch computations. So what is Krichever genus? So let X, now we assume X is manifold. And then it has a tangent bundle. So if X was a complex manifold, then it will have a complex tangent bundle. Right? But you don't have to be a complex manifold so the tangent bundle to be complex. All you need is some some way to multiply by I in this bundle. Even better, you can assume that this is, so this plus, since we're talking about characteristic classes, nothing's going to change if we add a trivial bundle. So we add some trivial bundle, some rank, and we assume that this is, here we assume it has complex structure. So in our particular has joint classes. So these manifolds are called stably almost complex. If your manifold has multiplication by I in its tangent bundle, it's called almost complex. If you add some copies of a trivial bundle has multiplication by I, then it has stably almost complex. So it has Chern classes, and in particular has a theta class of the tangent bundle. And so now, Krichever studied elliptic situation. We'll go to that in a second. So this is the we'll talk about K theory in a second. But what is this function? Every lecture in this, I think maybe every talk in this thing has this formula in it. So this is the theta function of maybe x. This notation here, x times z over theta of x times theta of z, and then you get more things if you like. But that's kind of so in fact you can kind of remove this for now. So this sort of expression. So what is this? How are we going to generalize this? Is it everybody have seen this a million times in this lecture? This sort of theta shifted by that. How are we going to generalize this? We're going to generalize it by saying that z will be, so z will take z to be an element in U1 or C star. And that will just act on it by multiplication. We'll tensor this tangent bundle here with the defining representation. So there's some bundle, some complex bundle. And this is a group. So if I have any bundle over any space, I give myself one more U1. And I can make it act on this because, scalars act on every vector space. So scalars act on any bundle over any space. That's kind of profound, that scalars act on any vector space. That's part of the definition of what a vector space is. Okay? So if I want to just scalar dilation, this is implied for any bundle. So I can take this bundle. It was as before, but now it equates with respect to one more group and this. So this means this has the effect of what? That whatever Chern roots of this bundle were, they will be all multiplied by z. So you had the structures in Nikita's talk. You had the structure yesterday that has something in the numerator and something in denominator, and exact same thing in the numerator, except in every term you shift by a variable. That's this kind of structure. What? Epsilon 3, right? So z is exponential. So that's z. Z is exponential of epsilon 3, or 2 pi I epsilon 3. You want some kind of integral structure, maybe 2 pi I.
Epsilon 3 takes values takes z of 1.
Anyhow, something like that. Yeah. So this is an even better formula. People will like the Euler formula that exponential of 2 pi I equals 1. And this formula has, the beauty of that, it has all the mathematical constants, 1, 2, pi I, and e. But this is even better, it has also 3. So then we define Krichever genus. I don't know.
All 3 and it's here.
Let's say what? No, this is equal to z. Z is also very important. Anyhow, so the Krichever genus of X, well, that's the push forward to a point. How are you going to define it? Push forward to a point. To the point. Okay. I'll write sort of. I'll just write the Euler curve. Euler curve you can some. No, I know. Push forward to a point. Push forward to map X to the point. You push forward under this map of the theta of Tx.
The function of Z.
It's right. This is depends. This is now. This is. This is where this lives in. Well, we will discuss. So it depends. This depends. Depends on Z and this new one variable and whatever was already acting on X. So in particular, the formulas you saw in Nikita's lecture yesterday. So this kind of and then yesterday had form of some kind of summation over R tuples of partitions, or was it N tuples of partitions? N tuples of partitions. Of partitions. And it had some kind of product, or some kind of boxes in this partition, and that will be theta of whatever something, and then something times Z. And what it is, it's the Krichever genus of, you take modular space of frame rank rank and instantons on C2. This is not exactly a special case of that. What does mean frame? Frame, you have everything's trivialized in infinity, so you have residual action on this framing. There's an action of, I don't know, Un. And on C2 itself, there's an action of U2. In this U2, you had variables kind of epsilon 1, epsilon 2. And this Un, you had variables A1. And the difference with the setup from we had so far is that here we assumed X is compact, but this space is not compact. And this is why this is an interesting function. Because main theorem of, so Krichever's rigidity theorem says, so what does Krichever rigidity theorem says? That on this variable, this does not depend. This is the rigidity. Upon some conditions. Upon some conditions, it doesn't depend on those variables. So if I take in K theory, this is the old theorem of Atiyah Hirzebruch. If I take it in elliptic cohomology, that's Ziegler theorem. Yeah, so this is, of course, he proved it when there was no elliptic cohomology, had a different proof. In the exercise, we have kind of direct proof. So in the exercises to the problem session, you can read the direct proof. You can do this exercise and have direct proof. So this is, but the main feature here is that if I have something compact, that's essentially trivial. Where this is not compact, and this is why it's interesting. So if there was, in other words, there's lots of young people here, many other people like I became old, thinking our whole lives about the question, is there a good way to compactify this space? If there's some good way to compactify this space, then that would make Nekrasov theory easier. Oh, Well, trivial, yes, trivial. And the main issue is that it's not compactifying C2. You can certainly compactify C2. The main difficulty is to compactifying this gauge transformation. That's the because you can somehow scale the bundle to infinity, and that's a bad idea. I mean, not a bad idea. We have to be something. Right. Anyhow, if you have some ways to compactify this moduli space, that'll probably get a lot of mileage in what Nikita is talking about. But like I said, I was thinking about this question since I was roughly your age and without much success. But you're smarter, the math progressed and so forth. So you can try it. Right. Yeah, so we'll get to that. So first let's do the K-theory analog of that. So in K-theory, what are we computing? So in K-theory, we're computing so let's analyze this in K-theory first. So in K-theory. What's this theta bundle of the tangent bundle? Well, in K-theory, it says times Z. What's it going to be? It's going to be 1 minus Z inverse the cotangent bundle plus Z minus 2 exterior power of the cotangent bundle, and so forth. Right? That's the Kazul complex. Take the dual bundle. And so the Euler characteristic, Euler characteristic of this theta, well, this will be the summation over I Z minus Z inverse to the power I. Now the Euler characteristic of on X of the ith exterior power of the cotangent bundle. So ith exterior power of cotangent bundle, that's our maybe K. Exterior power of the cotangent bundle. What's the kth exterior power of a cotangent bundle? Well, that's kind of holomorphic. Well, if my space is actually holomorphic, then it's holomorphic. Otherwise, if it has multiplication by I, that induces decomposition on the complexified tangent bundle, so on and so forth. So this is a holomorphic K forms. That clear? So for instance, if X is actually complex scalar, if X is a complex scalar manifold, then by Hodge theory, then Hodge says that the cohomology of, so what does Hodge theorem says? That in a scalar manifold, I can compute topological cohomology from cohomology of holomorphic K forms, right? So this embeds into ordinary topological cohomology of X, whatever C coefficients. Make sense? Example. So this is, sorry, let's just do an example. If I take IH top, in ordinary topological cohomology of P1 with maybe C coefficients, that would be what? This would be C, so to speak, C in dimension 0 and another copy of C in dimension 2. Right? And this corresponds to h naught of the trivial, the constant functions. So if I have a constant functions on P1 have cohomology, and this is this, and this corresponds to H1. So I look at the cotangent bundle to P1. Cotangent bundle to P1 is O of minus 2. And the first cohomology of O minus 2 is one dimensional, it's this thing. But now, how any kind of automorphism of P1 will act on this? Well, how it's supposed to act? So if it's automorphism of P1 a connected group, they cannot change the topological cohomology. So if I have a connected group on topological cohomology, it has to act trivially because any cycle will just move. Right? So it says that this space, this is a trivial representation. So automorphisms, this is a trivial automorphism of P1 module. And this is true in complete generality. If something injects into topological cohomology, then any connected group will act trivially. That makes sense? So, but this is a proof using Hodge theory. Of course, there's a much simpler proof, which we'll do in a second. What's the simpler proof? So suppose I have to prove so simpler proof. So this is also, I think, was known to IT and Hitze proof. Is that is the following. So suppose if I want to prove some function is a constant function in the group, it's enough to prove it for any one parameter subgroup. Right? So if I want to prove that some representation is trivial representation of my group, it's enough to prove for any one parameter subgroup I have a trivial action, right? So let S1 act on X, and let A maybe be a coordinate. And in the complexification, star into the complexification. So, and this is maybe called A. And just look at localization formula. What's it going to say? So if I want to compute Euler characteristic of X of this, well, I'll just write. I'll write the same thing, theta, Cx. Set. What's it going to be? It's going to be the Euler characteristic by localization. This will be the on the fixed locus. And now, on the fixed locus, if I take the tangent bundle to X, I restrict to the fixed locus, well, that will split into the fixed locus of the tangent bundle and the normal bundle, right? Okay, that's clear? So if when we restrict this theta to this fixed locus, we'll get a part which is a theta bundle for the fixed locus. So it will be theta of, sorry, this is not the theta, it's another letter. Where did I put the eraser? Ah, thank you. Yeah, that was kind of on the pushing the boundaries. Once it's up there, then it'll be kind of hard. So this is theta. So what's it going to be? Theta of this t the fixed locus, and z. And then, so this would be the part corresponding theta. Theta is, so if we add bundles, then theta is multiplied. Right? So that, then there will be theta of the normal bundle z times z. And then by localization, we have to divide by the theta of the normal. So where is the A dependence here? So there is no, so A does not act. It does not act on the fixed locus, it does not act on this part, it does act on this part. And so what is this thing? This thing is, in K theory, it's a, it's going to be, what's it going to be? It's a product. This is going to be a product of things. There's some kind of one, whatever in denominator, I'll just write Wi inverse. And it times, maybe times A to, let's just make it maybe specific. It'll be A to whatever power 5. Just some monomial in A, some weight of A. And then there will be the same kind of thing times Z. Okay. So now we look at this formula. So remember, right now we assume that F is compact. So this thing is a finite dimensional representation or virtual representation of A. Whatever the weights in the normal bundle, however A is going to act in the normal bundle, there's some kind of components in decomposition of the normal. Any power you want. Yeah, I put 5 just so to speak, for. Maybe I is kind of bad idea. Let's put. I don't know, something like that. I think. It just Wi is something, some Chern root of some other bundle, some equivalent variable, whatever was in the problem before we introduced it. But, yeah, whatever denominator, the numerator will be a copy of that when we shift by A. Right? So it's a finite dimensional representation of A. Right? So in particular, its character is all-around polynomial. So maybe I'll give myself a new board, since it's kind of an important point. So this thing, the character of that, this is a all-around polynomial. Polynomial in the variable A. Look at this expression. We see this has finite limit as A goes to 0 and A goes to infinity. Make sense? Well, I'm just saying that if I have a Laurent polynomial that has a finite limit as A goes to 0, as A goes to infinity, that Laurent polynomial is a constant. It doesn't matter. Just says that tells you Laurent polynomial. This tells you it's bounded at infinity. So it's a constant. If you compute them, it's a constant. But there's in fact, so that's the end of the proof. Both sides depend on A. What? And here A also appears explicitly. It's a recurrent bundle and some group acts on it. Okay. A will explicitly act there. But you can learn more from this proof. So this is, I'll just indicate, one thing you can learn from this proof is that if you let A go to, actually let A go to infinity, you learn something. Now, what is this? What's the limit of that? If you look at this expression, it says what? This has the property that this goes to, well, let's now spoil Kolya's notes and put some number k. What? You didn't try 5? Yeah. Yeah, that's exactly important. So this goes what? So if this goes to 1, if so let's say let's do specifically. Let's take a limit a goes to 0, and we'll also consider limit. We can also similarly consider a goes to infinity. The result should be the same because it's a constant. So, but nonetheless, if a goes to 0, then this thing, so k is some non-zero number because this is this actual weight of the normal bundle. So k, all we know about k is that k is non-zero because this appears in the normal bundle. The group actually has to act there. So if a goes to 0, well, this goes to where? This goes to 1 if k is positive, and goes to z if k is negative. And here reverse. No, just one term. I'm looking at one term. One term goes to this or this. And so if, as Andrei indicates, if I look at the whole product here goes to something like z to the power of number of repelling directions. Or so this is not actually attracting, because these are weights dual to this. This is the attracting directions. And here it goes, the whole product goes to the z times the number of repelling directions. So what is it? So if I look in repelling direction in the normal bundle, and this goes the attracting direction. So if I have some fixed point, and I have some group action, maybe a x on it. Let's say a go to 0. Now, as I go a to 0, some directions will be attracted to my point. Some directions will be expelled from my point. Right? So my action will look something like this. And so you get at every point you have some number of attracting and repelling directions. That's completely analogous. And in fact, if you consider moment map for this action, this will be exactly Morse theory. But otherwise, it's just completely analogous. How if you have a Morse complex, you look at the critical point, you look at the descending or ascending manifold, and you use this to understand cohomology. You from the number of attracting and repelling things, you can conclude something about the cohomology of your manifold. And exactly the same here. So if you're interested in want to compute some function in Z, we know it's a constant in A, but we can still use this action to learn something about it. Is that clear? Kind of an important point.
Could you please explain why you wrote the expression of small theta when you define it Krichever?
Because what's it going to be in elliptic cohomology? In elliptic cohomology, this expression this expression here would be exactly this ratio. So the elliptic cohomology will have to replace it by this, the exact analog of that. Right? This would be exactly that. Well, it. No, because but you it's like in Morse theory. If you study Morse complex for a function f and you study Morse complex for a function minus f, they look differently, but they compute the same thing. So if you're computing some Poincare polynomial, some Betti polynomial, then there's a different computation of the same thing. For compact manifold, yes, we're doing it for this rigidity works for compact manifold, and the reason it's like I said, the reason it's good to have for compact manifolds is because. I mean, it's not true for non-compact manifolds, but the difference, like the two non-compact manifolds may differ in the compact manifold. Right? You can do some geometric operation that kind of adds a compact manifold to non-compact manifold. We have some rigidity that proves that nothing changed. Like for instance, maybe we'll talk about it tomorrow. But for today, I just need to indicate what's the actual statement of Krichever theorem. So the hypothesis is just like if you, for those of you who remember Henry's talk last week, this hypothesis is going to be exactly like that. So assume.
Excuse me, can I ask a question?
Sure.
So it's somehow like a hyperbolic localization. And when you say that the multiplication is going to z to the power of attracting or repelling direction, is it like somehow upward flow over the fixed point?
So maybe I'm not sure I didn't get the answer. The question, but maybe I should say that this expression is this expression that becomes constant. It's a constant. You can take it out of the Euler characteristic for each component of the fixed locus. You can take it out, but if the component is not trivial, you can still have to compute it on the fixed locus. Right? So it says like if I want to know like Hodge, so some kind of manifold, and I want to know its Hodge numbers, and I have a group action, then I can construct the Hodge numbers of the ambient manifold from the Hodge numbers of the fixed locus and the knowledge of how many attracting repelling directions I have at each point.
So, Andrei, you need to know the number of cells in each dimension and which are attraction, something like this, right?
So all I need to know is what are the Hodge numbers. So if I want to compute the Hodge numbers, all I need to know is what are the Hodge numbers for the fixed locus, and at each fixed locus, how many attracting directions do I have? True. That's a true statement. No, not at the given point. It's a sum of all points. It's a sum of all points is the same. Yeah.
Which numbers are the number?
What I say is true for. This decomposition into this attracting manifolds is a true decomposition of Hodge structure. So the actual Hodge structure is like that, but we don't have to worry. So what's the actual theorem of Igor? So theorem, and I think it was published. When was it published? Like 90, something like that. Maybe Vasya knows. So I think it's 90. It's Igor by Krichever. Was rediscovered in 1991 by Hone. Yeah, I don't know. He wrote a Diplomarbeit in Bonn. This is a very, but this is the Krichever. This is 99. It's already in function analysis and applications, or were somehow published already. And it says the following. So suppose that the first Chern class of the tangent bundle is either 0 or the first Chern class is divisible by some number n, and and this variable z to the n is the root of unity. So we got assumption just exactly in Henry's talk, there was this kind of dichotomy. Then
This is the integer.
what?
This Chern class is the integer.
It's the first Chern class. It's an element in cohomology, and so this has to be either 0 or divisible. So this is in H2. This is 0 equals not just any 0, but the 0 in H2 of X. And similar, it's divisible in this group. Then, and X, right, X, compact, stable, almost complex. On complex. Then this then the Krichever genus is in fact rigid. Krichever genus of X is a function. It's only. What? Yeah, zero is anything, or if it's a divisible. So of course, 0 is divisible by anything. You can take any z, but if it's and so maybe in the interest of time, we'll give the proof of the first part. So this proof will be slightly abstract. But you want a concrete proof in exercises. Igor gave a concrete proof of this statement. And in exercises you can do this concrete proof. So what is the theta bundle? Theta bundle have a tangent, you have a manifold X, you have a tangent bundle of X. What do you mean I have a tangent bundle? Tangent bundle means you go to, so maybe of dimension n, you get to this BU and you pull back the tautological bundle here. And this is the Gauss map. This is the Gauss map from which we started at the beginning of the first lecture. And the theta bundle you pull back from elliptic cohomology of, so maybe I'll write it here. So, and then there's a elliptic cohomology of BUN, elliptic cohomology of maybe UN equivalent elliptic cohomology point. And here is the theta bundle, and you pull it back. You pull back by gamma pull back of theta. Theta is tautological. Get the theta out. So far, so good. So what is this thing? This has unordered n tuples of points in the elliptic curve, and this is the locus. Well, it doesn't matter what it is, but I just remind you that these are functions. That this is O of the divisor, where one of the points is equal to 0. Is divergent. What does it mean that that a first Chern class of my bundle is 1? That means that my Gauss, I'm gonna, instead of pulling back from BU, I'm going BSU. then what does this mean concretely? Then inside here, I have elliptic cohomology of SU over point, which is what? Which are the n tuples of numbers. So there's a, this is the kernel of the map. So maybe I'll write it here. So this is embedded here and gets this kernel of a map to elliptic curve, which is L1 point. This is the map that just takes a tuple of points and sums them up. Because if what was the first term class of a bundle? Your Chern roots, you just multiply them. So the inside here, so this is the locus of n tuples that sum to 0. So you're pulling back something from the locus of n tuples that sum to 0. But what is this map? So if I look at the elliptic curve, so if I look, in other words, if I take n tuples of points in the elliptic curve, these are the same as divisors of degree n. And then I consider a map, which are I take addition map. So P1, Pn. This goes sum of Pi's up to the curve. And I look at the fiber of this map here. What is that fiber? What is the sum of endpoints of the curve that sum to 0? This is if I want to define n tuple of points on the elliptic curve that sum to 0, that is the same. So I claim that this is a projective space of dimension n minus 1, because this is that's it here. Because what is it? These are the points. So what does it mean I have this map? These are points. Okay, maybe there's an exercise that you can find more details, but these are points that are, this is the linear system. These are divisors, linearly equivalent to the point. So to the point where all of these are 0. So the point n times the origin, n times the origin. So the points that sum to 0 on the elliptic curve, this is the same of divisor n times the origin, and I see how it moves. And these are this point. But any divisor moves in the projective. The way any divisor moves is always a projective space. So this is a projective space. And the point is that what? No, it's just in general for any the moving of any divisor is a section of some line bundle. So this projectization of sections of any divisor moves in projective space. So in other words, the set of points that are sum to 0 on the elliptic curve, that is a projective space. And you can check with 2 points. With 2 points, with 2 points, what you're going to get? You're going to get a quotient. So what's it going to be? About 2 points, 2 unordered points on the elliptic curve that sum to 0. That's the same as 1 point modulo plus minus. But the elliptic curve modulo plus minus, that's P1. Right? So whatever it is, this is projective space. And projective space has a wonderful, as opposed to that, projective space has a wonderful property that all line bundles on projective space we know. And they all come in discrete families. So if I have a continuous family of bundles of the same degree, they're the same bundles. Right? So this is says, so this is again the hook. This is this bundle theta of z times z. This is some kind of bundle. This is some bundle on elliptic cohomology of x. That bundle is pulled back from here. Here, I cannot move this bundle by z because it's a bundle of projective space. And I cannot move bundles on projective space continuously. It's going to be the same bundle. Right? So it says the bundle. So the conclusion is that, oh, sorry, I have to finish the proof. Maybe I'll write here, is that theta of txz is the same bundle. Oh, the theta bundle is a section, whatever, is a section of the same bundle as theta of tx. Because they both pull back from something when bundles don't move. And so therefore, the result is that if I have a section of some theta bundle and I push it forward, then I'm going to get, so this says that the push forward to a point of this is a section of the same bundle as the push forward of that. So it says a section of trivial bundle. Because if I set z to 1, then everything cancels out. So this, if I set z to 1, everything is all the numerator denominator cancel out. So if I set z to 1, then there's nothing to compute. So this push forward is therefore a function, like an actual elliptic function. But actual elliptic function is a constant. That's the end of the proof. Compactness is used in the very definition of push forward. We only define it for compact things. To define for non-compact things, you have to say some extra word. But of course, there's a concrete proof that says that you by hand check that under this condition you really get an elliptic function. I mean, it's not hard. You just check. In exercise, you can check that you write this expression. It really is an elliptic function. It has no poles, and therefore it's a constant. Okay, I'm over time, so I'll stop here.
Any questions?
So in principle, it depends on the covariant. If I have some group action on X, then it will depend on the covariant variables corresponding to that group. Right? The same, like in K theory. If I have, if I compute this in K theory, it'll be a function on whatever automorphisms of X I have. And in fact, so this says that in fact this function is constant. And you apply any automorphism of X, it doesn't change this function. Any group action. So it's going to be constant. Of course, constant, I mean locally constant. So if I have other components, this will be. If I have other components, but my groups is, let's say connected group. For any connected groups, it's actual constant. Then there's nothing to say. So if I have a trivial action, then I have a function of the trivial group, which is the constant.
this is moving into like a discussion for exercise sessions. Are there very quick questions? You can ask them during the coffee break.